On this worksheet, we're going to practice a few different problems involving writing and using equilibrium expressions. In this first problem, we're going to be writing the concentration equilibrium expression. That means that we're creating an equilibrium expression using the molarities of the solutions in the balanced equation. So concentration means that we're writing the expression using molarities. We can be really specific by calling this equilibrium expression a Kc, K, the equilibrium constant, and then the subscript C because it's calculated using concentrations. This is going to be, as you know, the products of the reaction, which are H plus and CO3, 2 minus, and each one needs to be raised to its stoichiometric coefficient. So since the coefficient of H plus is 2, we're going to put this 2 right here. We can leave off the states, so we're going to leave off the AQs. It's not necessary for us to have that. And then down here in the bottom of the fraction, we're going to put our reactant H2CO3. Products over reactants raised to their stoichiometric coefficients. The next problem, we're going to be writing a pressure equilibrium expression. So that means that we would call this a Kp with the subscript P for pressure. This means that we're going to be writing this equilibrium expression using the pressures of the gases that are in this problem. So we're going to start with our products. We have H2 gas. The way that if we're doing a pressure equilibrium expression, we don't use the square bracket notation. The square bracket notation is used to indicate the molarity of the substance. So when we have H2CO3 inside square brackets, that means that we're referring specifically to the molarity of the H2CO3 solution. So down here where we're using pressures, we're not going to use the square brackets. We're going to use partial pressure notation. So we'll do a capital P for partial pressure and then subscript the molecular formula H2. It does still need to be raised to a stoichiometric coefficient, so we'll put some parentheses around it with a superscript 2. Our other product is the O2 gas, and so again, we're going to do partial pressure of the O2 gas. For our reactants, we have H2O, but H2O is a liquid. So when we're writing equilibrium expressions, we do not include any substances that are in the liquid state or also in the solid state. They obviously don't have a pressure, so it wouldn't make sense to include it in this anyways because it's a liquid. And if we're talking about a concentration equilibrium expression, we don't include liquids because they're pure. We don't include solids because they're pure. Because they're pure, they don't have molarities. So it doesn't make sense to include them. So this particular equilibrium expression isn't a fraction because there isn't anything to put down underneath the fraction, or if it really bothers you and you really want to put something down there, you could put a 1 if you wanted, but that isn't mathematically necessary. Here is another one. We're writing this time a concentration equilibrium expression. So we're going to go products over reactants raised to their stoichiometric coefficients, leaving out the solids and the liquids. We have a solid, so we're going to want to leave that one out when we're writing this. Starting with our products, we have Cu2 plus, and its stoichiometric coefficient is 2. And then we have I minus, and its coefficient is 4. And then our reactant, the only one that we're going to include is I2, and its coefficient is 1. Now for this next problem, we're going to actually do equilibrium constant calculation. So we've got some pressures and then an equation, and we're being asked to calculate the value of the equilibrium constant. The first step in doing this is writing the equilibrium expression. So I'm going to begin by writing the Kp equilibrium expression, products first, so the pressure of HBr raised to its stoichiometric coefficient times the pressure of O2 raised to its stoichiometric coefficient. I left off the P there. And then our reactants, the pressure of Br2 raised to its coefficient, and the pressure of the H2O also raised to its coefficient. So once I have the equilibrium expression established, then I can go along and plug in the values of the pressures that have been provided in the problem. The pressure of the HBr is 77.2, and we want to remember that we're going to raise that to its stoichiometric coefficient. The pressure of O2 is 15.4, And with all of these, the value of the equilibrium constant, whether it's a Kp or a Kc, it's a unitless number, so we drop the units off these numbers as we're entering them into the equilibrium expression. The pressure of Br2 is 90.3, and that gets raised to the 2. And the pressure of H2O is 88.9, and that gets raised to the 2. And then now we just have to actually work the math out on this. 77.2 raised to the 4 times 15.4 divided by 90.3 raised to the 2, and also divided by 88.9 raised to the 2. This, I'm getting 8.5. And so now we have some questions asking us to interpret the values of the equilibrium constants. So this tells us that the equilibrium constant for this reaction, we don't know if it's a Kp or a Kc, but it doesn't matter. The equilibrium constant is 0.0067. At equilibrium, will there be more CO or more CO2? It might be helpful to write an equilibrium expression, so I'm going to go ahead and do this over here. CO2, I'm just going to assume that this is a Kc. Again, it doesn't matter if it's a Kc or a Kp. Products over reactants. So what this is telling us is that when we're in equilibrium, when we plug in the numbers of all 4 of these molecules, the outcome of that is 0.0067, which is a small number. Specifically, it is less than our cutoff of what constitutes a small number, which is 0.01. Since it's less than 0.01, that means that we would consider this to be a small equilibrium constant, a small k, or a Kc or Kp, whatever you want to call it. And this means that the reaction, we say, favors the reactants. Mathematically, this means that the amount of CO2 and H2 is very small compared to the amount of CO and H2O. If you think about just the math that's going on here, we're taking a small number and we're dividing it by a large number, like maybe 1 divided by 100, only it's even more serious than that, more significant than that, like 1 divided by 1,000. So the quantity of CO2 and H2 is very small compared to the quantity of CO and H2O. And that means that at equilibrium, there will be more CO than CO2. Because we have a value of K that is less than 0.1, which means that the reaction favors the reactants. The majority of the substances are the reactants. What is the equilibrium constant for this reaction right here? Refer to problem number 5. Okay, so if we look at this balanced equation right here, compare it to the balanced equation in 5, we can see that this equation has just been reversed. So CO and H2O, instead of being written as reactants, they are now being written as products. When you reverse a chemical reaction, you also invert the equilibrium constant. So for the reaction up above, where we said that K was 0.0067, and then that came from the equilibrium expression CO2 times H2 over CO times H2O. Well, if what we do is we swap the direction of the reaction, so now our equilibrium expression is going to be CO times H2O over CO2 times H2. What we've done here is just swapped or flipped that fraction, and then that means we're going to do the same thing over here to our equilibrium constant. Might be a little bit more helpful to think of that as a fraction, and then that means that we want to swap this fraction as well. So if you reverse the direction of a chemical reaction, you invert the value of K. The value of K is going to be 1 over 0.0067, whatever that works out to be mathematically. And then here is one more pretty similar problem. What is the equilibrium constant for the following reaction right here? So again, we want to take a look at the relationship between this equation and the equation that is in problem number 5, which is right here up at the top. These substances are in the same order, so our reactants are still reactants and our products are still products, but we have changed the stoichiometric coefficient, so everything has been multiplied by 3. So again, we want to think mathematically, what does that mean? For our original equation, if it was 0.0067, and that came from CO2 times H2 over CO times H2O. But if we come along with this and we change the stoichiometric coefficient, so now it's CO cubed, H2 cubed, CO cubed, H2O cubed, we need to do the same thing to our equilibrium expression K. So this is going to be 0.0067 cubed.